Hopefully it comes up soon. Good. So what we have covered so far is related to the object-oriented programming concepts. And we went into abstraction, inheritance, polymorphism. Now we want to apply this a little bit. So this lecture works, well, first of all, it serves Lab 5, which you guys, well, I mean, I know you have been busy with Lab 4, but you will be starting soon, or if you have already started. So it serves Lab 5, but also works as a good link between 2SH and 2SI. So we don't cover, 2SH is not a data structures course, right? So it doesn't cover in detail different types of data structures and the essence of them, but I wanted to give you a flavor of how do we apply the concepts we have learned, including pointers, including classes, including constructors, class members, etc., into implementing a certain data structure. So we'll go through this in the lecture. Last tutorial has already covered this a bit, but again, with more connection to the lab, is how to really implement a set using a linked list. So we will go through an example, hands-on example together during the lecture, and hopefully this will help you also continue the example and apply it to the lab. Good. As I said, the lectures has already the lecture slides have already been uploaded to Avenue. What is a linked list, right? Or in a sense, in fact, maybe one step back. What is a data structure, right? So going back to to one of the pillars of object-oriented programming, how do we separate or decouple abstraction for implementation? So I will give you one important example that you do in Lab 5. So we have what we call, let me enable the pen here. That's not good. Again. So is that a PowerPoint problem again? Come on. It keeps running. So let's see if that's really okay. Then just reopen it. Where to find that should be somewhere. Come on. Okay, so until it comes up, let me know if you have questions or concerns. So let me utilize this 1 minute or so until it comes up to address anything. You know that today is the deadline for Lab 4, right? And you know that Lab 5 due date is basically the new due date is December 8th. So hopefully that helps. Okay, so here linked list going full screen. Enabling the pen. And go back to Teams and share screen. Okay. Good. So basically one step back. So there is what we call abstract data type. Abstract data type. This is usually what people start discussing data structure as well. What is an abstract data type? The first word is abstract. So you can think of it's something that has to do with the abstraction pillar of object-oriented programming. To understand or have a taste of this, you know that in Lab 5, we are implementing a set, right? What is a set? A set conceptually is in fact a math concept, right? For example, an ordered set or a sorted set. It's something that has nothing to do with how you implement it. This is what we call an abstract data type. So it's a data type that is abstract. It's not associated to an implementation. And then what you are doing in Lab 5 is to implement it. So basically, this is the abstraction, which is the ADT. And then we are implementing it using a linked list, which is a data structure. Right? So ADT is the abstraction side of things, right? Which is, again, in our case, it's just a math concept here. While how do we implement it? You implement it using a certain data structure, which is, for example, using linked list, right? This makes sense? So simply data structure is how you materialize implementing some abstraction data types. And as you can see, sets can be implemented using a linked list, or they can be implemented using arrays, for example, or queues or stacks. You will discuss different data structures in 2SI. But simply the idea is you want to implement an abstract data type, something that is simply is a concept, for example, a mathematical concept, right? Set or a sequence, right? And then when you implement it, you start saying, oh, how do I implement right now? What data structure to use? What operations I perform? And the example for this is Lab 5. So hopefully the difference between the abstract data type and the data structure is clear. Again, it comes from the decoupling of abstraction from the implementation, right? You can think of data structure is the actual implementation of things. Great. So a linked list is a data structure. This is why when we say, well, linked list is data structure is basically you have some implementation in hand, like in your mind, something like I have a node and then a pointer to the next node. So you start already thinking in implementations. When I told you a set, well, set kind of should invoke in your mind concepts that are not associated to implementation. For example, is this a sorted list, non-sorted list? What order do they have? A sequence, non-sequence, etc., etc. The main benefit of a linked or the main feature of a linked list compared to an array, for example, comes from the fact that linked list is a dynamic data structure. So the idea is that its size can in fact change during execution. In an array, we statically define the full size from the compilation time, right, from the source code. While in linked list, I can keep adding nodes there, right? I can keep adding elements, entries to the linked list. So it's a sort of dynamic, which has the advantage of they don't have to be back to back in memory. Remember, we have already discussed these things before. They don't have to be back or contiguous in memory. The size is only what you need, right? And simply how to, if they are not back to back in memory. So here I have my memory. For example, I defined one entry here, another entry here, a third entry here because they're not back to back. But now these are distributed entries. They are not really combined or composing one data structure. How to make them compose the one data structure is to make a pointer from each node or for each entry to another entry, right? This is why linked list is a data structure of one node or multiple, and they are connected using pointers to the subsequent nodes. And then you have to keep track of this, as we will see, which means you have to keep track of the first node, what we call the head. And then the last node, to know that this is your last node in your linked list, you basically have to terminate it. Its next pointer would be null because you don't have a subsequent node. Kurt, please go ahead.
Is there a way to mimic this a little bit in C by using pointers to structures? I know,
yeah,
obviously.
100%. Yeah, okay. Yeah, that's a good point. In fact, you can implement a linked list in C because all the concepts we're discussing right now, in a sense, has nothing to do with classes, right? So I didn't really come to the point that this node is a class or this linked list is a class. I didn't say that, right? It's just a data structure. In C, we don't have classes, but we have structures. So that's a good point. So usually, if you Google, for example, how to implement a linked list in C, you will find that people are defining a structure of a node, which has a node and a pointer to the next node. Remember, in structures, we can have a pointer to the same structure type, right? And then you link them basically to implement this linked list. So that's a very good point. Thanks, Kurt. Yeah, as we said, it's dynamic because it can grow or shrink during execution based on insertion and deletion, and it can be as long as you require, as far as you have a place in the memory. And in that sense, it doesn't waste your memory space. And here is one visual example of, I have a linked list of 3 nodes. A is the head node, C is the last node, so it points to a null. That's why I must keep track of the first node, and the last one is just simply pointing to null. So this kind of ground here, it means it's null. Good. How to keep track of a linked list? I need to keep track by knowing the pointer of the first entry, because everything is a chain. Everything is connected to each other. So if I don't track the first one, I lose track for everything, right? And a big advantage, the main reason why people are using linked list over array is for types of implementations that you want to do a lot of insertions and deletions. Because think, for example, if I want to have something, for example, the set that we do in Lab 5 using arrays, but I want to do a lot of insertions and deletions, but I still keep the order. How do you do this in an array? The idea is each time you insert an element in a certain place, you need to reorder the whole array and shift elements one by one. So it takes a lot of time. In the data structure terminology, this takes an order of n. What does it mean with an order of n? My writings are just appearing slowly here. It's interesting. Doesn't appear at all. Wow, that's quite interesting. You guys see a static slide as mine, is that correct? Oh, now it appears, okay. So what do we mean by order of n? You discussed this a lot in 2SI, but the idea is that if you have an array of order n, oh, it's too much delay. It's coming now. If you have an array of size n, in worst case, this insertion will take you n operations, because assume, for example, you are inserting at the beginning of the array. That means you need to shift everything else afterwards. So it takes n operations. While insertion and deletion in linked list is just a constant time, as we will see right now. Because it's dynamic, I can just manipulate the pointers and I'm done, right? Good. So again, the main advantage, or when you think of when to use a linked list versus an array, the insertion and the deletion, if there are a lot of operations for insertion and deletion, linked list is the way to go. Here is a sample code of how to implement a linked list. Simply, we have 2 classes. One is called the node class. The node is nothing other than a class that is holding the actual data of this entry. So one node is one entry in a linked list. And then the pointer to the next node, as I mentioned before. And then if I want to implement a linked list, I need to keep track of the head, which is of type node. And then I have my methods simply that do the insertion, deletion, printing, navigating, or traversing the linked list, right? And then I have, this is a constructor that simply says initially the linked list is an empty data structure. So let's quickly, in fact, jump into online GDB and try to, well, let's open another one. Okay, so I have a node class. And then class node. Just simply, it's just a very simple class. So it has, well, my data, let's say it's an int data. And then my next node will be of node type. This is called the next pointer. And then I have a linked list class. You can call it anything. And then I need to keep track of the head. What is the type of the head? Again, it's of type node because it will be pointing to a node. So in that case, I define node and then I call this head. But to be able to do this, well, again, I need to include the header file you should already be all familiar with this right now. It's if you are using a certain type here node, it will not be recognized until you include the header file. And then you can add your methods. For example, the constructor. What you do in this constructor, maybe just making the head equal null. And just make this public. And some other methods. Let's say, for example, insert or delete. But before insertion and deletion, let's do a quick maybe search, right, to traverse an element. So search will return a certain element. So it's int search. And then in that case, I will take, well, let me think, how do we want to do the search? Maybe just return something that is either 1 or 2 based on whether it's 1 or 0 based on whether it's found or not found, right? So in that case, let's make it bool, true or false. And then I will take data as an input, okay? So let's call this input data. So the purpose of this function is to search the linked list, right? Good, but I need to be able to insert elements, otherwise I will not really have any linked list initially. So in that case, I will have insert, so it's void insert, and then I will take input data as an input as well. Okay, so the idea is how to implement the insert now. Let's first add the linked list.cpp. So I will start with the insert. So in that case, we said it just returns void, and this is linked list class, and insert. But here, I should include ll.h. Then it takes int input data. Come on, data as an input. Okay, so how do we insert? So let me visually show it to you first. Assume this is my linked list that I showed you earlier. So this is generally the status of a linked list. Initially, it's empty, but that's a special case. Something that you learn in data structures a lot is you need, in fact, to think of what is the common case, implement it, and then add additional code for the corner cases. So let's ignore the corner case of an empty list for now. Let's say, and also maybe insertion at the end, right? Because there's also another special case. And let's say that generally I'm inserting something in the middle of that. What the middle doesn't mean really the exact middle, but something in between, right? So what do I do, right? Just visually think about it. Assume you want to insert a node between, let's say, A and B, right? In that case, you first need to define your node itself, right? You would have a temp pointer to it. This is the point you need to insert. So this is the item you need to add to your linked list. And then, because I want to insert between A and B, you need to break the link between A and B. Make A, instead of A next pointing to B, I will need to make it point to my new node, and then make the new node point to B, right? That's in fact all the steps you need to do, and these are constant time steps, as you can see. So you don't have to shift, or so there's no variability in the time here. One very common mistake I see, which will break everything, is that you have to make sure you make basically your point to B before you make A point to X. So what I mean is, let's call this new node, okay? New node. If you have done it in the steps I just told you, which is make A point to X, so do something like this. You break the link between A and B and make A point to X. How do you make X point to B? In fact, there is no way, because you lost access to B, right? Because the only access you have to B is the pointer that was from A to B, right? So in that case, you need first to make that point to B, and then move that pointer from here to here, right? So if this is a bit confusing, let's jump to the code and see really how it works, right? But before this, okay, so maybe because we need this, we have an empty list at the beginning. Before this, let's discuss some of the corner cases visually as well. What if I want to insert something at the beginning. So this is your head. What do you want to do? Well, if you insert X at the beginning, then X have to be your head. But again, if you moved the head to X before you make X point to A, you lost access to A. So the steps would be, first, leave the head as is, make X point to A, and then move the head from A to X. Right? So in fact, inserting at the beginning is very simple. The second corner case, what if initially you didn't even have a head, you have a null? Well, that's in fact even easier, because in that case, you don't have any of this, right? You just have an empty list. In that case, well, you will make the head instead of null point to your point, and your next point should be null, right? Because in that case, that's the only node you have in your list. So this is the second corner case, which is you are inserting for an empty linked list. The third corner case, and then I will stop for a second, take your question. The third corner case is if you are inserting at the end, something here. In that case, this is a null pointer, so you can make this one point to this one and make this null, right? So it's also easy. So at a certain point during insertion, X and A point to B. That's correct, Stefan. That's correct. Because you want X to point to B before you remove the A pointer. That's correct. Kurtz, do we implement insertion in the class methods or in the program? That's also a very good question, Kurtz. So both are possible, right? So if you want a class of linked list that has all the methods that are really manipulate or utility functions of a linked list, then you implement them as member methods inside the class itself. If you want to implement them outside of the class, then in that case, in fact, you need the insert. For example, what if you want to implement the insert in the main? In that case, you have to take the linked list as an input and the new node as an input. And then your output should be the new linked list, right? Because insert is not now a member function of the class. So it doesn't have access to the linked list by default, right? So that's the difference. So from a functionality perspective, both are possible. What I would say is more professional is, in fact, you have one class that would have all the methods, but you might be tested, or maybe in an internship question or something, it's still a valid implementation that you have a method in the main that operates on a data structure. So it takes linked list as an input, for example. And it's a good thing. You might also think, for example, of how do you do it, right? And hopefully if we got time in coming lectures, I might just show you an example as well. Good, but try it at home. If you had questions, please ask, right? Good. If there are no further questions, let's really see how do we reverse a linked list. Yeah, that's excuse me. That's a more advanced question, Stefan. So reversing means, well, make it from here to here. In that case, it's not easy for a singly linked list. We call this singly linked list because each point, each node only has a pointer to the next node. There is another data structure that is called doubly linked list. Each node is pointing to the next and also pointing to the previous. So reversing a doubly linked list is much easier because in fact, just already there, like the order is there. You just take the head from here, put it at the end, and make this point to null. But like single linked list to be reversed, it's a bit involved, right? So let's take things step by step. Let's first discuss the insertion, deletion, and then we will. If you are interested about reversing, you can in fact do it using the methods we do. For example, take every single node, put it at the end, right? That's one possibility. Or create a new linked list but in reverse order. Okay, so now let's assume I want to insert. So we said the general case is, in fact, I'm inserting something in the middle. So in that case, first of all, I need to define a node pointer, right? And this is my new node. Good. And then new node. So in the node, this was let's say it for now, for ease of discussion, this is public, okay? Just to make it accessible for ease of discussion. So in that case, I can say new node, but generally you have to make it protected and then use getters and setters for this. But then you say new node and then data, And in this case, this will be equal to your input data, right? So now you set your data, you need to set your next, right? So my next is something that in fact I don't know yet, right? It depends on where I'm inserting, right? Assume you have a sorted linked list. So you insert in a certain position, or how to implement. There are different ways of implementing insertion. For example, insert at a certain node number. But let's say I have a sorted linked list, for example, right? In that case, you want to insert in the correct order. How to do it? Well, you will have a loop. So let's say while my current, well, those next not equal null, for example. Okay. Or even the current itself, in fact, not equal null. What is current? Now I need to define, well, current of this thing. I need to start my current to be the head. This is how you can have a node traversal. You start your current from the head and you keep increasing your current at the end here. So you say current equal current next. And then now I'm going through my current. So initially my current is pointing at the head, right? What do I need to do? I need to compare the data if it's a sorted list, right? So I would say if current dot data is, well, let's say it's an increasing order. So here I would say my list is in increasing order. So in that case, if the data of the current is increasing order, means you need to find the node that is larger than, let me think. It's a bit problematic when you do the increasing order. So let me go back here and show you what I mean. Is there an empty slide? Yeah, here. So let's look into if I want to do this. So assume I'm having a linked list of increasing order. This has the value of 1, 2, 3. And assume I want to insert, or let's say 1, 3, 4. And I want to insert 2, right? So visually, you know that 2 has to come here. But how do you know this? Your current here is, as far as it's less than this one, then you are in the correct order. But if your current becomes in a node that is larger, then you know you need to insert before. So in that case, it might be better to check the current next, not the current itself, right? So in that case, if current, and in that case, you also have to be current next, not equal null. If current next the data is, what did we say in the example? Well, it's larger. So if it's larger or equal your input data, then you know that this is where you want to insert, right? Simply that's the idea, is that I keep searching my node until I find a node that has a value that is larger than or equal to my node. But it's the next node because I don't want to lose the pointer to that node, right? In that case, you need to do the insertion here. So you need your node, we called it new node, dot next to equal the current dot next, right? In our example, if I go back here, this was my current. This is current next. You want the new node next to be the current next, correct? Did you get that? And then you need the current next to be the new node. This is how, in fact, you do the insertion. And then you make the current next to equal new node, just new node. Does this make sense? So this is the actual code that does the insertion. The loop itself is doing the searching, right? Let me stop for a second, take questions, because I know this might be a little bit convoluted for some of you. This makes sense? In fact, there might be easier versions of doing insertion. Here I started with the example of a sorted list and you need to insert something in the middle. But let's say if I have, but let me first, if there are questions. Okay, so what if I'm I make an easier version, which I call insert beginning, for example. So I want to insert always at the beginning. In that case, it's an easier function to implement because it just considers the special case or the corner case we have talked about. So I'm always inserting at the head, right? So current is the current node. Current next is the what current is pointing to. That's correct, Stefan, which is the next node to that. That's correct. If you feel a little bit confused with this insert, let's first consider the simpler cases first, right? Assume I always want to insert at the head of the linked list at the very beginning, right? So what to do? Again, the first thing is I need to create my node. That's the first step, right? So it's basically this step is called node creation, right? No, I'm always advancing. In fact, in this case, I'm done, right? So in this case, I can just break, right? So this function is not fully implemented yet, Curtis, right? But simply the idea is once you find your node, you no longer need to search because this is a sorted list, right? But here I'm always incrementing for that while loop, right? Okay. Okay, good. So this is basically the node creation. So assume I want to insert at the beginning. So I created my node. Then, because I'm inserting at the beginning, which means my new node will be the head. But if I move the head to the new node, I lose access to the original head, as we discussed before. So the second thing is to set node next to head, right? So in that case, you will say new node next equal head, basically, right? And then now you already have your head secured, right? So you already made your next is the head. So now it's good to move the head. Move the head. Good. So now you will say head equal new node. I guess that's simpler for you, right? So this corner case is a bit simpler. So let's stop here and see if there are questions. So I have done 3 steps basically. I created my node, which you'll always need to do, then set the node next to be the head, and then move the head, right? If there are no questions here, let me ask you a question. Does this handle the special case of an empty list? Yes or no? What do you think? Yes, of course. Why that's the case?
I don't see my mic on for this one. I think it's because when we're to make the head, we if it's an empty list or set, then when we initialize it, the next item is going to be null, and that's what we want anyways when we're initializing the new head.
Exactly. Thank you so much. So simply the special case of an empty list is that the head is null. But in fact, if the head was null, which is linked list was empty, that means my new node will be the only node, which means its next will be null anyway. And then I update on my head as I usually do. So the head is no longer null. So that's correct. So it already handles a special case of an empty null. Good. So let's add this to our functions here. I'll call it insert at beginning. Good. So then let's also add another one for the other special case, which is insert end. Okay. Let me just call this insert at beginning. Okay, at beginning and then at end. And then here, always insert at beginning. So if I want to insert something at the end, so well, again, this code would just remain exactly the same. I need to create my node first, regardless of where to insert it. Good. But if I'm inserting at the end, what should I do? I know that my last node is in fact what I call the tail node, is pointing to next. One problem is I don't in fact have a pointer to this last node, right? I only have a pointer to the head, correct? Which means you need in fact to traverse the linked list to go to the tail. So in that case, you need to do a node traversal, right? A linked list traversal. So you say while, so first of all, you have a current equal your head, and then you say while current dot next is not equal to null. What you do is you just advance your pointer. So just again, a very simple traversal. I started from the head and I keep, as far as my next is not null, I keep moving forward. So when do I stop? When my next is null. Okay, what does this mean? In fact, the tail node is the one where its next is null. That means your current now, by the end of this loop, will be simply your tail, right? So here, move to tail node, right? This tells us something that in fact, it might be useful in your linked list class that in addition to keeping the head is also to keep a tail, right? Sometimes linked list data structures do this, keep the tail for you, right? But that has the problem is that each time, in fact, you update, you need to update the tail as well, right? But anyway, now we traverse it for the tail, so we are in the right place. What do I do? Well, I need my node to be after the tail, right? So that means right now, my current next should equal to my node, right? Correct? Because, well, let's really visualize this. So if I'm here, I want to insert at the end. So originally, here is my current, and my current next is just null. I have my new node here. If I want to insert my new node at the end, what do I do? Well, something I can definitely do is to make my new node equal to null, but this will come by default for now, as we will see. Simply, you need to make this one point to this one, correct? So you need to make your current node equal to the new node, and then you make the new node next equal to null, right? Another way to do it is to say, well, I can make my new node equal to current next, which is null, and then you make my current next equal to my new node. So it's the same two steps that we have done in the general insertion here. Correct? So here, simply this will be setting your new node. So this will be setting to set node next to null. And then step 3 is this one. Which basically means move the tail, right? Make it your last node. Questions? So we have seen insertion at the beginning and insertion at the end. Insertion at the end seemed a little bit more involved because we needed to traverse to get the tail. We didn't have it from before. Questions? Is there any question? Okay, good. So now, if I'm assuming a sorted list, and this is just simply, let's continue with the example we have covered. Again, I created my node, so this is basically node creation, right? This is our step 1. And then here I'm traversing to find, because this is an order one, so find the position to insert 2, right? And then once you find it, you just break here. So there are multiple possibilities here. The first one is, what if in fact your node was larger than all the nodes in your linked list, which means it need to be the tail. In that case, you will end up with your current at the tail, right? So in that case, you can still insert. So you'll just say new node equal new node as next, similar to what we have done before, right? But how to know this? So simply you need some sort of a flag, right? Or simply don't do this here and do it at the end anyway. So how does this work? Let's explain. Let's wait for a second and explain. So I have two possibilities. Again, what I'm doing, I'm searching for the place to insert. If the place comes in the model in the point in the middle, that means this condition will become true, right? Because you found a place where the coming node is larger than you, so you need to be before that node. In that case, I don't do anything. I just break because I only need the current next to point into it, and then insert my node here. So this is step 2, finding the position. This step 3, do the insertion. The second possibility is, what if I really didn't hit this condition at all, which means my node was larger than all the nodes in the list. In that case, you will not hit the break, but you will exit the loop with the current equal to the tail, basically, because the current next will be null. In that case, you still want to insert at the end, right? This is basically, it will work fine. Good. There is a third possibility, which is, what if your node was smaller than all the nodes? So it's the smallest, basically. So it has to be inserted at the beginning. So in that case, let's see what happens. Your current is equal to the head, but you are only checking your data of the next. So you are skipping the head checking, correct? So that means for this special case, handle the special or the corner case of comparing with head, right? Because here you don't compare with the head at all, right? So in that case, you write something like if well, in that case, it can be current or head because they are both the same thing, but you can say if head.data. Why I'm writing dot here? Because this should be also a pointer thing. So it should be current next data and node new node data. That's correct. Good. So in that case, you say if head data is larger than or equal to input data, that means that it's the corner case that your node should be at the very beginning, at the head, right? So this is the corner case of the head, that the new node should be before the head. Well, what to do? In this case, in fact, I can use my other function and do the insertion at head, right? So just say insert at beginning, right? And then, but in that case, I don't need to create a new node. So I don't need to call this function because I've already created the node. I can just say, well, maybe use some of the code here. Make your, just simply take these 2 lines of code, which are this step. Just simply make your new, make your next is equal to the head and then move the head, right? Is there any other special case we are missing? What do you think? Are we missing? And I will conclude with this. So the whole function today was about linked list and insertion. So on Tuesday we'll be doing the deletions. But let me ask: are we missing any special case for this general function of insertion? This is a bonus mark question. Null linked list, Stefan. Exactly. Thank you. So that, again, please send your name to Shuruk. So another question is how to handle it. So now, what if we discussed 3 special well, 2 special cases and 1 common case. We're inserting in the middle, so that's good. We're inserting at the end. We're inserting at the beginning. We are left with the case that you have an empty linked list. So what to do in that case? If you have an empty linked list, then in fact you can handle everything even from the very beginning, right? So you can handle the special case from here. Once you created your node, you can say here, if head or current, basically, both are the same thing, equal null. In that case, that's empty linked list, special case. So I might just say handle the corner case of empty linked list. So what to do is I have already created the node. The only thing I need to do is I make my head equal to this. Well, in fact, I can just do these 2 steps as well, exactly, because the head is also null. So let's do that. We just take this and put it here. I'm making my head updated, and my new node will be equal to head, which is the null. But this tells us something, right? What does this tell us? Is in fact these 2 corner cases, they have exactly the same piece of code, right? Right, which means inserting at the beginning, including the null. So in fact, I could combine them by saying if the head data is larger than or equal, or the head is equal to null, you just do these 2 steps. So you can combine these 2 if statements together to have a more compact code in a sense. Make sense? So we'll be done for today's lecture. It's all about insertion, but let me wait for a couple of minutes to take questions, and thanks everyone.